Hello students, I am Dr. Tanmoy Biswas. I welcome you all in my channel Chemistry the Mystery of Molecules. Today's topic of discussion is one very interesting topic. More reactive substance is more stable. Is it really possible? We say more reactive means less stable. Less reactive means more stable. So is it really possible? Actually student, it is possible. I shall explain that thing. But before going to details, one MCQ. I request you, please pause the video, try by yourself, and whatever answer you get, please write in the comment box along with few words as your explanation. I believe you have tried, so let's start the discussion. So first we will select the point like reactivity of alkene, and in this case we shall discuss substituted alkenes are more stable or more reactive. Isn't it a contradictory? So let's learn. If I take a simple alkene like this one, here you can see that it has alpha hydrogen allylic. So this CH bond can participate in hyperconjugation with this alkene. How that is possible? Let's look at here. So this CH bond, this sp3 CH bond, there are two hydrogens here. So this sp3 CH bond participates in hyperconjugation. How? One pair of electron is delocalized into the pi star of student this carbon-carbon double bond. And in this way, the canonical form should look like CH2 minus single bond CH double bond CH2, and there is a H plus. By the way, never get confused that sir, is this H plus completely free? It is not completely free. It remains close proximity with this carbon. So this is hyperconjugation, and that's why hyperconjugation is sometimes called no bond resonance, because in this case this bond is actually broken, but it doesn't go away from this. So what is the conclusion? Because of this hyperconjugation, you can say more the number of alpha hydrogen present with respect to alkene, more electron density is gone. And another thing, these, if more number of CH present, they will participate more in hyperconjugation. And remember one statement, because of this hyperconjugation, more delocalization will be obtained, and more the delocalization is equal to more stabilization. So from these we can conclude one thing: if alkene is more substituted, that will be more stable. So you can see this is ethylene and this is tetramethylethylene. So this part is more substituted. 4 substitution are there. So you can conclude this is more stable, and more stable because of these hyperconjugation. So stability of alkene is dependent on hyperconjugation, and hyperconjugation means delocalization. Delocalization means stabilization. So it is more stable. Now, because of hyperconjugation, there is another factor arises: electron richness. How? See, previous structure, you can see some electron density, I mean CH bond electron density donated to this pi bond. Two types of donation possible. One is student plus I effect. How it works? The sigma donation through this carbon-carbon bond. If you look at this carbon, let me take it here. This carbon is actually sp2 hybridized, and this carbon is actually sp3 hybridized. sp2 carbon have higher electronegativity than sp3 hybridized carbon. There is one question, student. This between sp3ch, sp2ch and spch, who has higher acidity and why? I have discussed previously this thing. I request, if you know the answer, please write in the comment box. Now let's go. So plus I effect possible, one thing through sigma bond, and another thing hyperconjugation. So because of this hyperconjugation, this alkene became more electron rich. So if this alkene became more electron rich, then obviously it can react preferentially with electron deficient molecule like electrophile. Agree? So that is actually the story here. You can see the reactivity of alkene increases towards electrophile due to electron richness, and that electron richness arises because of this hyperconjugation. So overall, what summary we learned, that the electron density of this CH sigma bond participates in hyperconjugation, a type of delocalization with this alkene, and a stabilization is obtained as a result of such kind of delocalization. Okay, because delocalization results stabilization, and because of this delocalization, the double bond became electron rich, so it became more reactive for electrophilic addition. So because of hyperconjugation, it got delocalization, got stabilization, and because of this it became electron rich, so it became reactive for electrophilic addition reaction. So it's a little confusing, isn't it? But it's the truth. But this statement, don't make this statement as a general statement, because if you change the substitution pattern, or if you change the nature of the reactant which is reacting with this double bond, then you can obtain different results also. For example, nucleophilic addition to pi bond. So if you take this one, this is electron donating group methyl, it's attached to this CH3. Now it is nucleophilic addition. Nucleophilic addition means nucleophile will get attached or added across this CC double bond, and nucleophile is student electron rich. So because of these plus I and hyperconjugation, both these alkene is actually electron rich. So it will not react preferentially with this nucleophile. Why? Because it is electron rich, nucleophile electron rich, so they will repel each other. So electron donating substrate doesn't make these pi bond more reactive for nucleophilic attack. So this is less reactive. But if you take another electron withdrawing group, I mean this carbonyl, so what happened? It became more reactive for nucleophilic attack, and nucleophile will attack here, this carbon. Why? Because of this resonance. Let's draw it here. This is a CH2, single bond CH, this is double bond O minus, this is R. So here there is a plus charge. Plus charge means electron deficiency. That's why nucleophile will preferentially attack on this center. Actually, nucleophilic addition is dependent on this nature of the substitution. This statement's proof is here. I've already uploaded a dedicated lecture on here. You can see nucleophile addition on alpha beta unsaturated carbonyl compound, which is the thermodynamic control product and which is kinetic control product. Or another example, Grignard reagent where R is the nucleophile, where it will attack. This is 1, 2, 3, 4. 1, 2 addition means addition across this carbon oxygen double bond, or oxygen and this carbon, where the addition will happen. Please visit these videos so you can have a better learning. By the way, please check the I button and description box of my every video. So there are lots of related lecture you may find there. Now let's go to our second example, that is butadiene versus isolated alkene. We know butadienes are more stable compared to isolated alkene, because in case of butadiene, I mean CH2, there is a conjugation among the pi bonds or p orbitals. Okay, we know conjugation means stabilization, so that's why butadiene is more stable. And you can see with respect to a single alkene, butadiene is, or 1,3-diene, more specifically if I say it's not a butane, it's a 5 carbon 1,3 pentadiene. So this is more stable. You can see this. How this comment is met? By heat of hydrogenation. Before going to that, let me give you another example. You may think, sir, there is a 1 alkene, 1 pi bond, so this is fine. And if you have 2 pi bond but they are not in conjugation, because this carbon is sp3, so there is no conjugation at all, but this is not that much stable like this butadiene. Question, why and how we can get this heat of hydrogenation value? So you can see here, what is heat of hydrogenation? Amount of energy released upon hydrogen addition to pi bonds. And what is the product? Product is this carbon hydrogen sigma bond. We know the sigma bonds are more stable than pi bond, that's why energy is released. This is exothermic reaction, and here the value is minus 127 kilojoule per mole. So if you take butadiene, means just add one another double bond. So what do you expect? That okay sir, 127 multiplied by 2, 254 kilojoule per mole, an amount of energy is expected to be released upon this hydrogen addition or catalytic hydrogenation. But how much is obtained here? Only 239. So 15 kilojoule energy is missing. Why this is missing? Because of stabilization. How can you explain this thing little differently? So this is reaction coordinate and this is the energy axis. So you can see here, this is the reactant, product is same for everyone, that is butane. So this is 1 butene, and you can expect this is the expected energy for butadiene. So you can expect, okay, this is the energy release for butadiene hydrogenation. This is the energy release you can expect for this butene hydrogenation, and butadiene's energy is actually here. And why this much stabilization? Because of delocalization or resonance. This is 15 kilojoule per mole. So if the reactant is actually stabilized at the initial stage, then during the reactant's conversion to this product, the output energy or energy release is expected to be lesser. So that's why instead of 254 kilojoule per mole, 239 kilojoule per mole energy is released. So this is the proof that butadiene is actually more stable than isolated alkene. If you have taken isolated alkene, for example, just as an example I am giving this one, then your expected energy obtained should be closer to 254 kilojoule per mole, because this is a sp3 hybridized carbon. So in these two double bonds there is no resonance, but in case of butadiene or 1,3-butadiene or 1,3-diene, there is a resonance. That is the responsible for such kind of stabilization. But Is butadiene really stable? And let's see this example. If you take butadiene and react with sodium liquid amine, this is nothing but Bart's reduction. What it produces? It produces alkene, isolated alkene. 40% is actually trans, so this is trans, and 60% is cis alkene. But this is simple alkene, isolated alkene. No further reaction doesn't happen. Further reduction is not possible. From this statement, I can say butadiene is more reactive than simple alkene. Okay, now question, why reaction stopped at alkene stage? Because alkene is less reactive than butadiene. So isn't it contradictory? Just some time before I told that because of delocalization butadiene is more stable than alkene. I am saying butadiene is more reactive. Why this? So let's learn the fundamental from this. So this y-axis, this is actually the energy axis, and this is the energy of a pi bond, and this is actually the pi star. Agree? So if you take any isolated alkene like ethylene, so you can expect this is the pi energy, this is the BMO, bonding molecular orbital, and this is ABMO, anti-bonding molecular orbital. For ethylene there are 2 electrons which remains in this BMO. But if you look at butadiene, so here 2 electron, here 2 electron, they are in conjugation. So these 2 bonding molecular orbital can participate in further conjugation. Consequently, what happened? They conjugate and produce 2 different, another new molecular orbital, and this is, here it is mentioned as pi 1, pi 2, pi 3, pi star 3, pi star 4, or sometimes people write psi 1, psi 2, psi 3, psi 4, both are accurate. Now here, since this BMO has 2 electron on each, so that's why these 2 orbital have 2 electron each. Now previously it was the bonding molecular orbital for a case of ethylene or isolated alkene, and this was the HOMO. Okay, so HOMO's energy was lesser. Right now in butadiene, HOMO energy is higher. Who will react with electrophile more efficiently? Obviously this butadiene. Why? Because electrophile is more energy molecule, less stable, carrying charge. So butadiene's energy and this HOMO energy matches closer, so that's why butadiene reacts with this electrophile. Or even, by the way, very soon I shall discuss a dedicated lecture on butadiene's reaction. You can see that better in that video. So butadiene will react more efficiently with these electrophile rather than alkene. That's why butadiene is more reactive for electrophilic addition reaction. Next, or you may consider as hydrogenation, similar type, but mechanism is different, but you can expect like that. But if you look at another way, so if you look at this anti-bonding orbital, 2 pi star conjugate together. So here 1 pi star, here 1 pi star, they combine together and produce this psi 3 star and psi 4. Now this is actually LUMO. By the way, HOMO means highest occupied molecular orbital, and LUMO means lowest unoccupied molecular orbital. So this is the vacant orbital actually, and vacant orbital's energy is less compared to alkene. So that's why it can accept electron density very efficiently from any nucleophile. Or if you look at Bart's reduction, then electron as the nucleophile, so it can accept electron, which cannot be done for isolated alkene because its antibonding molecular orbital's energy is higher. So right now I guess you understand why reactions stop at alkene stage, why butadiene reacted but alkene cannot react, why the reaction did not occur further. So that is the reason. So why this unique reactivity of butadiene is obtained? It is more stable because of delocalization, but it is more reactive. More stable because of conjugation. Conjugation is stabilization. But why reactivity? If you try to react it with an electrophile, it will react preferentially. Why? Because HOMO's energy higher. If you want to react this with a nucleophile, reaction will be more efficient. Why? The accepting orbitals or LUMO's energy higher, such that nucleophile can donate electron density efficiently. So for this situation, this is a win-win situation for both sides, makes the butadiene molecule very reactive for both type of reactions. Now, in conclusion, what you have learned today, that it is relative statement that who is more reactive and who is less reactive. Okay, and these conclusions should be made based on what type of reaction we are talking, what type of is my reagent, and what type of pathway it is expected to follow. So don't never say more delocalization, more stabilization. It is not always true. There could be some exception. So this one confusing statement we have discussed on today. So let's go to our MCQ. Now, which statement is true about this molecule? Now let's read the option. This is actually 2, this is 1 2 3 4 5 6, so 2 4 6 trinitro iodobenzene. Okay, now here all CN bonds are same length, means carbon nitrogen, these 3 bonds they are talking, and shorter longer like. So let's learn. This question should be addressed based on steric inhibition of resonance or ortho effect explanation. Means iodine, if you look at, it's attached to this benzene ring. We know halogens are orthopara-orienting and deactivating. Why they are orthopara-orienting? Because they can donate their electron density in this benzene ring. So ortho position first, and second in para position the electron density increases. Okay, now if you keep electron withdrawing group like nitro in the ortho and para position, this delocalization became better, or it facilitates, and halogen, this iodine carries a positive charge. We understand this much. Now here question that where delocalization will be better, in this ortho position or in para position, that could be explained based on this steric inhibition of resonance point of view. Means this iodine, student, it is actually a big atom. Look at, carbon belongs to the second row, iodine belongs to the fifth row, so there is a very big size. So this big atom attached here, consequently because of this increased size or steric effect, these two nitro group forced to have out of planarity arrangement. Okay, since they are out of planar, then what can happen? They cannot delocalize the electron density coming from this iodine. I mean these electron, if I say these electron could not be delocalized efficiently. Why? Because in order to delocalize this electron, these NO2 need to become in the same plane, which is not possible due to the larger size of this iodine atom. So that's why delocalization is not possible in the ortho side. However, if it goes to here, electron density will come here, means para position. If I draw it, it should look like this. So this is N double bond O minus, plus charge on nitrogen. Remember, nitrogen cannot extend its valency more than 4. So plus charge and 2 nitro here. Now these negative charge can participate in delocalization with this nucleus. Why? Because here such kind of steric inhibition of resonance not there, because 2 atoms are hydrogen. So it will come, it will open. So you can have the canonical form looks like this. So means delocalization is more through this NO2 group by formation of this carbon nitrogen double bond. Now one thing, student, if I say carbon nitrogen double bond here, means bond order more the bond order, shorter is the bond length. Means if you compare carbon nitrogen single bond versus carbon nitrogen double bond, so this carbon nitrogen single bond is actually longer than the double bond. So, and furthermore, CN more the bond order, means double bond if it is there, it is stronger obviously than the single bond. So these are the two message we can have it. Now here what statement about this molecule is true? All CN bonds are same length. These two versus this ABC, no, that's wrong. CN bonds of A and B shorter than C, no, A and B longer than C, because resonance not possible if position A and B because of steric inhibition of resonance. So this is opposite statement, wrong. CN bonds of A and B are longer than C. Yes, this is right. And all CN bonds are purely single bond. This is not true, because sometime before I have seen this canonical form. These results are partial CN double bond. So all are purely single bond. I cannot comment on this. So not, this is wrong. So option C is the right answer. So this is the overall discussion. I believe this video may be useful. Thanks for watching. See you in my next video. Bye bye.